بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله. This is a continuation for the gasket heat exchanger. Last time we are at this stage where we would like to calculate the heat transfer coefficient and the pressure drop for gasket plate heat exchanger. We defined previously the beta angle, which is the chevron angle. We also defined the vertical distance LV and the horizontal distance here is LH, in addition to LW and LP. The port dimension is DP. Also, we defined that LW is LH plus DP, and the vertical dimension of the plate is the vertical distance minus the port diameter. Projected area is LP times LW for the plate, but because of the aggregation, the developed length divided by the projected length is phi, so the plate heat transfer area then is the projected area times phi, where phi is the enlargement factor, which is more than 1. Here it shows the dimension again. This is one plate, and this is another plate down, and the distance from the center line to the inside surface of the plate is B, which is very important dimensions for calculation of Reynolds number. If you add P to the thickness of the plate, you get P. If you have several plates together compressed and the total compressed length is LC, if you divide LC by the total number of plates, you get the plate spacing P. If you subtract the thickness of the plate from P, you get what we call the P, which is half the width, which is very important characteristic length. The hydraulic diameter for the flow between the plates is defined as 2B divided by phi, where phi is the enlargement factor, as we said before. In order to calculate the heat transfer, we are going to use the same relations that are in our textbook, which says that the Nusselt number, this is Nusselt number, equal to some constant CH multiplied by Reynolds number to the power n multiplied by the Prandtl number to the power 1/3, in addition to the viscosity correction factor. The value of CH and n, as we're going to see in table 11.6, these two parameters depends on the chevron angle beta in addition to the Reynolds number. The Reynolds number can be defined by the mass flux GC for the channel flow multiplied by the diameter of the hydraulic diameter divided by the viscosity. GC can be found by dividing the mass divided by the area of flow area, which is B times LW, divided also by NCP, where NCP is the number of channel per pass, and it is going to be found using this relation, which says that NCP equals NT minus 1 divided by 2 NP, where NP is the number of passes. So for example, if you have, say for example, you have 51 plates total, you subtract 1, so you get 50, divided by 2 multiplied by NP. If you have one pass, then NP is going to be 1. If you have two passes, NP is going to be 2, from which you can get NCP. Once you get NCP, you can go back and substitute in the expression for GC to get GC, and then find the Reynolds number using this relation. Of course, the channel area is B times W, where P, as we said before, we defined it before, is half the width channel, and LW is the length that we defined previously. Table 11.6 gives the two values CH and N based on two parameters, the chevron angle beta and the Reynolds number. This is table 11.6. As we can see here, the table itself, the first column is chevron angle. If it is less than 30, 45, 50, 60 and greater than 65. The table actually is divided into two parts. This part, the first part, is going to give you the heat transfer, meaning the two parameters Cn and N, CH and N, and also it gives the pressure losses in terms of Reynolds number and the two parameter Kb and M. For the heat transfer, in order to get the CH and N, you need to enter this table with two information: the beta, how much is the value of beta, which is the first column, and then the Reynolds number. For example, if you assume that you have a beta of 45 and your Reynolds number between 10 and 100, then this is the HCH and this is the value of N that is going to be used in the previous relations that we in the previous slide. Also, for the pressure calculations, as we are going to see later, the two values which are Kp and M are also function of the chevron angle in addition to the Reynolds number. So if you have, for example, a Reynolds number of say 200 and the chevron angle is 45, then this is the value for Kp and this is the value for N as M as we go. We are going to see how to find the pressure losses using these two values just in a second. The overall heat transfer coefficient for gasket plate heat exchanger can be found using this expression without fouling. This is the UC, but you can also find the overall heat transfer coefficient for fouled heat exchanger. The total pressure drop for gasket heat exchanger is going to be the summation of the pressure drop in the channels plus the pressure drop in the port, which is delta B total equal delta B channel plus delta B port. The pressure drop in the channel can be evaluated using this expression, which is 4 times F multiplied by the effective length by number of plates, mass velocity square for the channel, and then the hydraulic diameter, the density, and the correction factor for the viscosity. Here we are going to assume that the effective length is equal to the vertical distance. The friction factor is evaluated using this expression, which is you need the Kp and M. These two values can be found from table 11.16 based on Reynolds number and beta value. So if you know the beta value and the Reynolds number, you go to table 11.6, you get these two values Kp and M, then you evaluate F and then go back to this expression to find the pressure drop for the channel. For calculating the pressure drop in the port, the author of our textbooks is suggesting this expression, which is delta B for the port is 1.4 times the number of passes multiplied by the mass velocity for the port. Be careful, this is not GC, this is GB square divided by 2 multiplied by the density, and the mass velocity is equal to the mass flow rate for either of the flow channels or flow stream, divided by pi d squared pi 4, which is the cross-section area for the port. Then you add these together, the pressure drop in the channel plus the pressure drop in the port, to get the total pressure. Here we'd like to just show you that how to calculate the mass velocity if you have an arrangement with only single pass. So for this arrangement we have seven plates as the effective number of plate. The total number of plate is 7 plus 2, so in total is 9, and the effective number of plate is 7, which is 9 minus 2, and then The number of passes here for this situation is 1 because the flow, all of it goes once from here to here for the cold fluid, and this is also 1 pass to go the other side for the hot fluid. In order to get the NCP, which is required in this expression to find the mass velocity, we use this expression, NCP equal N total minus 1 divided by 2 multiplied by number of passes. For this situation, we have N total is 9 and we have number of passes 1, so you get NCP is 4. You can use it here in order to get the mass velocity, from which you can get also Reynolds number, and you go to the table 11.6 to find the heat transfer and the pressure drop. There is one example in chapter 11 in our textbook showing the calculations for gasket plate heat exchanger. The idea here is that you have water or wastewater in the fluid, the hot as a hot fluid, and cooling water as a cold fluid. The hot fluid enter at 45 degrees and exit at 45. The mass flow rate is the same for both of them, 140 kilogram per second. And the cold fluid enters at 22 degrees and leaves at 42 degrees. The maximum pressure allowed for both streams is 50 psi. The fouling factor is 0.0005. And then the properties, specific heat, viscosity, thermal conductivity, density, and Prandtl number for both the cold fluid and hot fluid are given. And it is also given some additional geometrical parameters for this gasket plate heat exchanger, like for example the plate thickness, which is T, and chevron angle, which is beta, total number NT, number of plates 105, the thickness is 0.6 millimeter, the chevron angle is 45, the total number of plates is 105, phi, the enlargement factor is 1.25, a number of passes, 1 pass for the cold fluid and 1 pass also for the hot fluid. The overall heat transfer coefficient clean is 8,000 and 4,500 for the fouled. The total effective heat transfer area AE is 110 meter square. The port diameter, which is dB, is 200 millimeter. The compressed length of the heat exchanger is 0.38 meter. The vertical distance LV is 1.5. The horizontal distance is 0.43. LW, which is actually LH plus dB, is going to be 0.63. The thermal conductivity of this steel is 17.5 watt per meter Kelvin. It is required in this heat exchanger to find to do the calculations and find exactly how much is the heat transfer coefficient and pressure drop, just so that the user or the student can train himself for the calculation for the gasket plate heat exchanger. Again, the solution is available in the textbook, but we are going to go through it very quickly to understand the procedure. If you calculate the Q, the heat rate, using hot fluid inlet and outlet temperature or mass flow rate, you get this value. If you use the cold fluid, you get this value, which are very, very close to each other. The hot fluid, as we said, 65 entrance temperature and the exit temperature is 45. The cold fluid is, again, the mass flow rate is the same for both fluids. And the cold fluid is entering at 22 and leaving at 42. So delta T logarithmic mean temperature is 23 because delta T1 equals delta T2 equals delta T logarithmic mean temperature difference. And as we said, the total number of plates is 105. You subtract 2 for the end plates, you get 103, the effective number of plates. The effective length that we are going to use to calculate the pressure drop for the channel is 1.55, which is LV. Since the compressed length is given 0.38 and the total number of plates is 105, we can get P parameter as we defined before. And then the channel length, or the mean channel gap, is equal to P, which is this value, minus the thickness of the plate. So you get the very fundamental geometrical parameter, which is P, is going to be 0.003 meter. You multiply P times LW, you get what we call the channel flow area that is needed in order to calculate the mass flux and the Reynolds number. The area for a single plate is equal to the total area divided by the number of plate, the effective number of plate, which is 103. So you get the single area for one plate is 1.067 meter square. If you would like to find the projected area, then it's going to be LB times LW. Both of them are given, so it's going to be 0.85 as projected area. But the total the area itself is 1.065 meter square. Of course, you can find out the phi as compared to what's given. So this is the definition of A1 divided by A1B, which is equal 1.25, which is very close to what is given, which is 1.25. Calculating the Reynolds number, you need to calculate the hydraulic diameter, which is 2B divided by phi, and you calculating now the number of channel per pass, also using the total number of plates divided by 2 multiplied by number of passes. We have only one pass here for this example. So the number of channel per pass is 52. This number is very important in order to find the mass flow rate in the channel. You divide the total mass flow rate, the whole, divided by 52, you get 2.69. This is for one single channel. If you divide this area, if you divide the mass flow rate divided by the area, which is the area which is equal to A of the channel, which is going to be P times LW, which is equal to 0.00189, you get the mass flux, which is 1,423.8 kilogram per meter square second. This value can be used to find the Reynolds number, and the same of course for the hot fluid and the cold fluid. So this value is 13,000 something, and the Reynolds number for the cold fluid is 8,000 something. You go to table 11.6. I'm sorry. You go to table 11.6, and according to the beta, which is 45, and we have Reynolds number in this range, you can go to the table 11.6. You get CH, this value, and N, this value. So directly you can use the expression for Nusselt number in order to find the heat transfer coefficient for the hot fluid and the heat transfer coefficient for the cold fluid. As you can see, of course, this term, the correction factor for the viscosity, has been neglected in this calculation. We found that the heat transfer coefficient for the hot fluid is this value, and the heat transfer coefficient for the cold fluid is this value. Of course, CH and N are the same because we are talking about the same very close Reynolds number, and beta value is 45, so that you can calculate the overall heat transfer coefficient, the clean one, using this expression. 0.006 is the thickness of the plate, and 17.5 is the thermal conductivity of the plate. You get 9931.5, that representing the overall heat transfer coefficient clean. You can also get the fouled utilizing the fouling factor total, which is given in the problem. So you get UF, which is the overall heat transfer coefficient for foul heat exchanger, as 6636 watt per meter square Kelvin. You can calculate the cleanness factor. You divide UF by UC, you get 0.67. You also calculate the QC and Q fouled utilizing U value that has been calculated, and you find that this is the Q clean and this is Q fouled. He divided this Q fouled divided by Q required in the problem itself, at the beginning of the example, you find that the Q found using the calculation, which is the actual value, divided by required value is 1.43, which means that actually you are getting heat more than what is required. The over surface can be calculated using this expression. Since we have RF total and we also know UC, you can get the over surface, which is 49.7 or almost 50, which is actually a large value. In order to calculate the pressure drop for both sides, the hot fluid and cold fluid, we utilize the Reynolds number that we found for each of them, and then we go back to table 11.6 to find the two values, the Kp value and M according to the beta and Reynolds number. So you get, for example, for this situation, you get Kp is 1.441 and M, which is going to be 0.206. You have to check that with table 11.6. Once you found these two friction factors, you come back and you can go back and calculate the pressure drop in the channel, and you find that the pressure drop for the hot fluid is going to be 272.087 Pascal. Converted to PSI is going to be 39.5. You do the same thing for the cold fluid, utilizing the same idea, the same thing, and you can find that delta B for the cold fluid is 42.3 for the channel. Now from here down, the pressure drop in the port as calculated. So you have to find GP, which is the mass flux in the port. You divide the mass flow rate by the cross-section area of the port. You get this value, which is totally different than GC, which is the mass flux for the channel. And then you substitute in this expression to find the pressure drop for the port, for the hot side and for the cold side. Convert it into PSI, so you get this value and this value. You add the values together, you get the total pressure for the hot side and the total pressure for the cold side. So you get 41.55 PSI for the hot, and you get 44.31 for the cold fluid as a total pressure drop, which is the pressure drop due flow in the channel and the pressure drop in the port. Of course, the two pressures actually are within the accepted pressure, because delta P max according to the problem statement is 50 psi. This is something that we'd like also to shed some light on. What the difference between the situation when you have one pass and two passes. This situation shows we have 11. Total number is 11. I mean the in total is 11 plate. This is in actually this is ineffective. So in total is going to be 13, because you have to add this one and you have to add this one also. Since you have two passes, if you can look carefully, you find that for example, the blue fluid is going this one pass and this another pass, and the same thing for also the hot fluid. There is one pass and then another pass. So you have two passes for the cold side, and you have also two passes for the cold fluid, for the hot and the cold fluid. In order to calculate the number of channel per pass, you use this expression. We used it before, but now since we have a number of passes 2, so we have to substitute here 2 instead of 1, because we have now 2 passes for each one of them. And in total, as we said, is 13, and NP is 2, so you get an NCP equals 13 minus 1 divided by 2 plus 2, which is 3, from which you can calculate the mass flux. And NCP now is going to be changed because the number of passes has been changed, and you from here on you can calculate the Reynolds number and the heat transfer coefficient and so forth.